Today we're going to look at the physics of music. So let's just start with the basics. So you've probably all heard of different letters when we talk about musical notes. So for example, we have A, B, C. Now these different notes correspond to a frequency. So A, for example, might be 440 hertz, B 494, C 523, etc. Now, the numbers themselves aren't really important to you at this point, but just know that each letter corresponds to a different frequency. So let's define a few things. We're going to define a chord is essentially two or more frequencies played together. And a couple of words, consonant and dissonant. Something's consonant if it sounds good, if it sounds pleasing. Something's dissonant if it doesn't. So let's listen to this in the action. So hopefully you were able to tell the difference between those two. If not, you might be what we call tone deaf, and this is going to be a hard unit for you. So who do you think is the father of all modern music? Could it be Mozart? Could it be Beethoven? In fact, it's a guy that you're definitely familiar with. His name is Pythagoras. Yeah, the triangle guy. So what Pythagoras noticed is that when he played um, notes that were whole number ratios to each other, the sounds sounded consonant, they sounded pleasing. So for example, if he had one string a certain length and another string exactly double that length, it would sound nice. So let's look at how that affects modern music. So we're going to look at two specific chords. The first one is what's called the octave, and the octave basically is the 1:2 ratio. So for example, if you have a note that's 440 hertz, if you double that, that would be 880 hertz. Or if you double that again, that would be, what's that, 1760. Or if you cut this in half, that would be 220. All of those would be exactly a 1:2 ratio to each other, and we call that an octave. And as you'll hear in a second, these notes actually kind of sound similar to each other, and so we give them the same exact name. So 440 and 880, we're both going to simply call them A notes. All right, so let's listen to some of these different A's and see if you can hear the similarities between them. And now let's hear the two A's together. So hopefully you're able to hear the similarities in those notes, and also that you would consider that consonant. So the last one I wanted to look at is the major chord. And the major chord has a nice 4:5:6 ratio. So for example, let's say we wanted to play C major. We start with the C note, which would be 262 hertz. To get the next note, we're going to multiply by the 4:5 ratio. So we'll multiply 262 by 5/4. When we multiply that, we're going to get about 327.5. And that just happens to be an E note. And if we do the 4:6 ratio, we'll multiply 262 by 6/4. And when we do that, we're going to get 393, which just happens to be a G note. So this would be, what's probably known as the most pleasing chord, the 4:5:6 ratio. So let's go ahead and listen to this one. So that's the major chord, and that one was the C major chord. There's a lot of other chords as well, but those are the only two, at least for this class, that I want you to know. All right, so one last thing with music we're going to look at is a term called timbre. And you've probably noticed, hopefully, that different instruments, even if you play the same exact note, they sound a little bit different. And so the reason for this is, well, let's look at this, clarinet, piano, and violin. So we have our fundamental frequency, which is the dominant frequency, but most instruments do not only play one, they play lots of harmonics together. So the clarinet, for example, you see the fundamental and then 1, 2, 3, 4, 5, 6, 7, 8, 9 other harmonics. And the piano even has more. So whatever combination of harmonics the instrument happens to play, when it reaches your ears, there's going to be some interference. It's going to produce a slightly different wave. So let's take a look at a picture of this. If we look at the flute, for example, the flute is really probably the most pure instrument. It has a very nice sine curve. Pretty much is just the fundamental frequency that's being played. But notice here the piano, the same exact note, and you would hear it to be the same. And in fact, if you look at the wavelengths here, they have the same exact wavelengths. But when you interfere all the different harmonics, you can see the actual waveform takes a slightly different shape. And the trumpet you can see is even more so. So you can see all these harmonics interfering with each other. However, again, if you notice the wavelength here, distance between here and here, here and here, etc., is going to be exactly the same. So all of these to your ear would sound like middle C, the same frequency, the same fundamental, but they would sound slightly different. Actually, not slightly, they would definitely sound different to you. And that's what we refer to as timbre. All right, so let's listen to these. Flute, piano, trumpet. So again, the notes are the same, but the timbre, the quality of the sound is slightly different. All right, I think that's it.